Okay, so what I wanted to do is I wanted to begin this conversation with the orbital component, right? So we wanted to kind of take a look at that. First of all, a little flesh that out a bit. And so that's kind of where we are now. And so remember, we defined orbitals as like neighborhoods within the overall electron cloud, right? So areas within which electrons will inhabit. It's kind of like you do most of your time in living in your neighborhood, right? And so you don't necessarily expect to find you in neighborhoods that are like not your normal place of living, right? So for instance, I'm in Southeast Denver, so you almost never find me up north, right? So that's because that's my orbital, right? Southeast Denver is my orbital. And so the same thing's true for electrons. And different electrons will inhabit these different orbitals. Now, when you take a look at an orbital, the important thing is, and I boxed it in and I started because this is an important thing to understand when we go to the next slide. And that is to say that by definition and by rule, in any given orbital, you can't have any more than 2 electrons. So basically, there's 2 electrons per orbital. And so that's basically what you have. Work with this thing. I should be muted. Now, when you take a look at that, then obviously if you've got like an atom with like a whole bunch of electrons in it, right, like 74, 75, or if you're gold, you got 79, right? The question is then, if you've got all these different electrons, then how do you organize these guys spatially within their neighborhoods, right? Since they obviously can't all be in the same place because you can only have 2 per orbital. So the question is, how do you arrange all 79 of these guys, right? So there's obviously a lot of organization that goes into that. And that's kind of what this piece is here. And so what you see here is obviously you see the Bohr model. That's for our own purpose and for our own understanding. And then you see kind of like the orbital idea here. Now, generally speaking, when we take a look at orbitals specifically, there's a couple of things we'll notice. First of all, the first orbital inhabits what we call the first ring. Now, what we want to do is we want to take a look. I want to use the Bohr model to sort of identify and to sort of characterize what we're talking about here. And then we'll take a look at the orbital component of it, okay? So generally speaking, when you're taking a look at electrons, not all electrons are the same. So each electron has its own temperament, its own personality, its own energy level. And so one of the things we want to do is sort of identify what kind of personalities electrons have and sort of where they belong energetically. So what that is to say, what neighborhood they belong in based on their temperament. Generally speaking, whenever you have an atom with multiple electrons in it, what you start doing in the Bohr model is you start diagramming these things out and you start organizing them by energy. Now, what I want to do is I want to use sodium, which is way over in the corner behind me. Most of you probably can't see it unless you're like from over there. You guys over here probably having a hard time seeing it because it just looks like you just kind of like got that fisheye lens kind of thing going on there. But sodium, for those of you guys who can see it, has how many protons? 11, right? And how many electrons does it have? Yeah, it's got 11, right? Because it's naturally occurring. So that's important. So let's go ahead and take a look and we'll just deal with the naturally occurring nucleus. We don't really care about the neutrons because we're talking about electrons now. We're not talking about the nuclear physics of sodium now. And so now we have these 11 electrons. So the question is, are all those 11 the same? The answer is no. Right, so let's go ahead and start characterizing these. Now, generally speaking, whenever you're building out an atom, the energy levels of the electrons are different. And that's what actually the rings of the Bohr model represent, is they represent different energy levels. So generally speaking, in order to build out a schematic for any particular atom, you take your electrons and you start building them out on these energetic rings. The first ring, which is that first innermost ring, is an energy level that we call N1. Now, in this case, they're using letters K, L, and M, and so forth. I typically use 1, 2, 3, 4 for reasons that are just more about clarity of notation, really, than anything else. Okay, so this represents your first energy level that you have in terms of the electrons here. Now, remember our definition. Our definition is that for every orbital, you can only have how many? 2, that's it, right? That's your max. As it turns out, within this first energy level, n equals 1, there's exactly 1 orbital or 1 neighborhood. So how many electrons can fit on this n equals 1? That's it. So for n equals 1, which is that innermost ring, the max is 2 electrons. But the problem is, are we done? No. How many electrons do we have left over? 9 more, right? So what do? We have to open up another ring, right? Which is going to have a series of orbitals in it. So typically from here on out, the rings are a little bit bigger. They can contain more orbitals. And at this particular case, this is going to be our n equals 2. Here, our max number of electrons that we can have overall in n equals 2 is 8 electrons. So there's only 2 because in that first energy level, there's only 1 orbital. And this is it right here. So here you can see we've basically opened up this first energy level, right? That n equals 1, right? And in that, you only have 1 orbital. It's a spherical orbital. They have a shape to them, just like neighborhoods have a shape to them, right? So it's a spherical orbital, which is one of the reasons why we refer to it as 1s. 1 referring to the energy level, n equals 1, s referring to its shape. So this is a spherical orbital. Now, if you take a look at this, it's not unlike that electron cloud, right? Where you kind of have that 3-dimensional density. This is kind of the same idea, where you have a 3-dimensional density within which this pair of electrons, because you can only have 2, can inhabit. So they're going to be somewhere in there. So what you're doing is you're kind of dividing your electron cloud up into smaller chunks. Okay. And this first level, 1s, is that first orbital. It's a spherical orbital. So these 2 electrons here are going to be basically inhabiting that little itty bitty sphere. Now, when you have the other 9, in the case of sodium, right, then they have to kind of be slotted in. So you have to create another ring, another energy level, because you've already filled up the one. You've only got that 1 orbit. And I know what your question is. Why do you only have 1 orbit? I don't know. That I don't know. That's a nuclear physics thing, and I'm not a nuclear physicist. But I know you're like, I thought you know all the answers. No, I don't. Not by a long shot. But there's somebody who does know that answer. Not me, right? So once you actually get to n equals 2 in this ring, now you have not 1 orbital, but 4 orbitals. Okay, so if you take a look at the lowest orbital, you have a 2s. So that is to say you're in the second ring now, 2, and you have your first orbital, which is spherical. Notice it's a slightly larger sphere than the first one. Okay, and you're going to have exactly how many electrons in there? 2 electrons. Now, the next group of orbitals are kind of related. They are the p orbitals. Shaped kind of like peanuts. And the p orbitals will basically inhabit all 3 dimensions of the axes, x, y, and z, right? So for instance, here's one along the x plane, here's one along the y, and here's one along the z. Each one of those is an individual orbital. So how many orbitals or how many electrons can this orbital contain? And how many can this one contain? And this one? 2. And how many altogether in the second level can we have? Right? We have 2, 4, 6, 8. 2 spherical electrons and 6 p electrons. Okay, for a total of 8.
On that second ring, will be adding 6 electrons
to the p orbitals. Yep. After adding the 2 to the s. So you fill up the s first, and then you start overflowing into the p's. Okay. So now, am I done? So let's take a look at what this looks like in the Bohr situation. In the Bohr situation, I fill this up because I've got 8. So 1, 2, 3, 4, 5, 6, and 7, 8. Am I done? No. What do I have left? I had 11 electrons, right? And how many do I have diagrammed out? So I've got to do what? Open up another ring, right? So now I'm going to open up another ring. That's going to be n equals 3. So that's my third shelf that's opened up. Guess what? The max for this one is also 8, right? Because now what you have is in this one, in n equals 3, I'm going to put it down here. You have 3s and 3p, right? So p has 3 versions of the same, right? So you have the 6 here. So you have all 3 of these in that p shell. So, whoops, I wrote this backwards. Right? So you have the same thing going on with that third outer ring. Now, obviously, you've got room for how many? For 8 more, right? But how many do you have left over? 1. So you got room to grow, don't you? Is that a good thing? Only if you're growing. Treat it like shoes. If you're a kid and you're actively growing, is it good to buy shoes with a little bit of room to grow? Right? When you're an adult and you buy shoes with a little bit of room to grow, is that a good thing? No, because you're gonna have a lot of foot problems, right? So these are all grown up atoms. They're not growing. So that's, and you can keep going for as many as you go. So you can imagine how many rings you've basically created for the 79 electrons that are going to be found in gold. Okay. And so you just kind of keep diagramming these guys out. Now, when you put all these together, then what you get is this kind of smash together. So all these exist together. So you have your 1s, your 2s, and your 2p, and your 3p, whatever, right? These all basically get crammed together around the nucleus. And that's what kind of creates your cloud. So here you can see what this looks like. When you cram all these little neighborhoods together, these orbitals together, they kind of create this sort of really weird kind of blobby looking electron cloud. And that's kind of where that statistical fog comes into play. Okay. Obviously, the more orbitals you add in there, then the more like a sphere that becomes, right? As you add more orbitals in there. Now, when you're taking a look at this, one of the important things to always understand is the relationship of what's going on here. And the reason why I like to stop and pause, because this is actually a pretty useful idea for us here in biology, right? Because a lot of times the question will come up, and actually I think Antonio asked the question last time after class, is the idea of like, okay, this is great. So we got all these electrons whizzing around in here in all these different neighborhoods, but then what happens when they all kind of come together and to converge together, right? Because you don't have these guys separated out together. All these people have to live together in the same city, so to speak, right? In the same electron cloud. So how do you actually sort yourself out in that sense? Well, what happens is these orbitals up here are kind of like the ideal world. This is basically what you would look like if you had nobody next to you and you just sort of lived on your own. But then when you start to come together with all these different other electrons are living in all these different other neighborhoods, so to speak, all these different orbitals, then you kind of have to do a little bit of sharing, don't you? I mean, if you've anybody who lives in a city knows that you have to have a little bit of tolerance for the fact that there's people living around you. If you live in an apartment, you have to have a little bit of grace for the guy upstairs, the guy downstairs, and the 2 people on either side. If you're in a garden apartment, I apologize. I feel bad for you. It's the worst place in the world to be. The only place to go from a garden level apartment is to the grave. And half the time you're already halfway there. I did actually. So I know exactly what it looks like. I remember that's where I was in grad school. I actually lived in some dump of an apartment that was up there on just north of Colorado and 9th. Really close, like within walking distance to that Royal Palace Motel, like the Crackhead Hotel. Yeah, where you take your various individuals of one stripe or another, most of which is not legal. And that's where you are. So yeah, you can imagine what it's like living in the garden apartment there in an old rundown building where everybody's plumbing problem was yours. Because you come home after a long day in the lab in grad school to carpets that are completely soaked. And like you look around, you're like, my toilet's fine. My plumbing looks good. So I must have just been gifted with the sewage of any number of individuals above me, most of whom I don't want to know, certainly not at that level. So yeah, that happened numerous times. Or like looking out your window, which literally is like this, right? So you're literally like looking like directly at somebody's grill and then watching cars getting stolen, like from your apartment window. Yeah, needless to say, back in those days, I used to own a gun. And it was actually helpful, to be honest with you. I'm not a very violent person, but yeah. What?
I wouldn't trust you with a better Walmart.
Yeah, I know, right? Yeah, see, that's why I always declare that I'm a Raiders fan and then I'm a Californian. So if you grew up in the neighborhood I grew up in, gun training is necessary.
You're from California? Did you say that?
Yeah. Yeah, so I grew up in not the fun places in California, right? So just north of Oakland. If you've ever been to
22nd and
Oakland,
Jackson,
what?
22nd and Jackson, I grew up in.
Yeah, I was north in Pinole.
Oh, shit.
Yeah, so I was basically right down the street from the Bloods. So gang awareness was a thing. When you're like from first grade to fourth grade, it's like the primary skill you learn is gang awareness. You know, who's around you, who's active, what's going on, who's doing a turf war, those sorts of things. So you get used to it. It wasn't so long ago that Oakland was the homicide capital of the world. So that's East Bay, right? So I hate it and I love it all at the same time because I still have a firm hatred for West Bay. So I hate it to see the Niners do well in football because they're West Bay and they got all the money and we got all the prisons. So we got San Quentin. So that's great. Right? So, or whatever you want. Which actually that's my East Bay humor coming out. Usually when I say San Quentin is in the East Bay, usually what I really mean is it's a city in the East Bay. Oftentimes I'm picking on Oakland. Because we definitely, or Pinole's not so great either. But anyway, so nice to have an East Bayer in the house. So now you understand. So Shane will be like, yeah.
Bear with me, so I'm pretty confused. That circle with all the dots is like equals 11, and that's the electrons
For sodium.
in sodium.
Mhm.
And so each layer, it only can have so many what are the dots?
Those are the electrons.
Electrons. Why?
Because it's easier just write E than writing E negative. So it's just notation, the dots. What do you mean, why? Why what?
Like, well, because I see like it ends up as 11. But you don't have 11 just on one.
No.
Because you're making the layers. I guess I missed.
And the reason you don't have 11 on one is because by definition, each orbital can only have 2. And that's one of those particle physics definitions. You have to get deeper, like way in the rabbit hole of quantum mechanics to define that. That's in biology, we don't get that far. Right. So the fact is, on that first ring, that's an energy level.
Yeah.
You only have one orbital, the s orbital. And so you only have room for 2 because there's only 2 electrons per orbital. That's why there's only 2 in there. So if you have more, you got to open up another energy level, and that's n equals 2. Okay. Now from here on out, you've got 4 orbitals, right? You've got 1 s and you've got 3 p orbitals. So you can stuff 8 electrons, right? So 2 per orbital. 4 times 2 is 8. So from here on out, as you go out, so if you get n equals 4, n equals 5, n equals 6, n equals 7, so forth, then all of that, so you're 8, 8, 8, 8 from here on out until you fill everything up. Make sense? So in that second ring, at this particular point, we had 9 left, right?
Yeah.
So we had more than 8, so we filled that second ring up. So that was done. And we've filled up all of our orbitals, so we're done there. So now we have to open up a third energy level in order to find some place to put that last electron. That make sense?
Yeah, thank you.
Now, if we had like more, then we'd fill that one up and we'd open up a 4th. And we'd fill that one up and we'd open up a 5th. And we'd fill that one up and we'd open up until we finally got less than 8, right? To where we had less than 8 left over. And then we just kind of fill in the leftovers in that last one. That makes sense? So like I said, notice what I'm saying. I'm not saying these are spatial arrangements. I'm saying these are energy levels. So what we're doing is we're diagramming out the different energy personalities of these electrons. So the energy personality of the second shell electrons is not the same as the first. And it's not the same of the third and so forth. Okay. This here is kind of a fleshing out of that Bohr model, the schematic, organizing the electrons by personality and by energetic level. This here is more like what it's really like. They're inhabiting more of a spatial orbital type of a shape within the electron cloud. Okay. And this is basically where you get to your electron cloud. Once you assign all these electrons into their orbitals, then they all come together and they form this giant electron cloud. Now, as it turns out, obviously, and this is a really good point because Antonio made this one after class last time, right? But the idea is you have a couple of things going on here, right? So you have the attractiveness of a positive nucleus pulling electrons in toward it, yes? Then you have the repulsion of like charges pushing themselves away. And in this particular case, the electrons, right? So when two electrons come close to each other, they repel each other, right? But at the same time, they're all being sucked into the nucleus. So what keeps them from crashing? I think that's actually your exact question. Actually, right? What keeps the electrons from crashing down into the nucleus? Well, it's simple. It's their repulsion, right? Because if we were all a bunch of electrons and we were all converging to the same point, at some point, we're going to get close enough to each other where the attractiveness that I have toward the nucleus is going to be overcome by my repulsion by my fellow electrons, right? So we're going to feel each other more than we feel the nucleus. And we're going to be like, oh, wait, I'm too close to another negative charge. So we're going to push off from each other. That also means that we're not going to get any closer because as we get closer together to each other. So we're never going to get that close to the nucleus. So it's our own interaction with each other, right? That repulsion of two electrons to each other that keeps them from crashing down into the nucleus. Exactly, right? And not only that, but there's more electrons here than just not, right? Because remember, this is a schematic of energy levels. But in reality, it's a three-dimensional spatial thing that these electrons are feeling. So even though, let's say, for instance, I'm an N=1, you're an N=2, different energetic level, you're a totally different type. And let's say you're an N=3, okay? So what's going to happen is we can, even though we're energetically on different levels, in space, we can all get to the point where we converge right here. So here we have 1, 2, and 3 right next to each other, right? But here's the thing. We're all negative, which means we're also going to be feeling each other's repulsions. We're going to be pushing away from each other. So that kind of balance between, okay, I'm going to push away from you guys because we're all negatively charged. So right about there. That's good. That's good spacing.
And that's what sends them back to the orbit.
That's what gets them back to their orbit. And not only that, but that's also what keeps them in their neighborhood because they kind of get this sort of elbow room thing going on where they're like, you know what? I'm okay with where I am. I'm okay with our kind of social distancing thing going on here. And let's keep it at that, right? So that safe personal space kind of a thing going on. That's what electrons do. And then what they do is they sort themselves out. And when they do that, their cloud forms this specific type of a shape. Okay, that's something that actually will shape the molecule itself. And that's important because shape is everything in biology, especially the proteins and things like that. Right, that basic idea that I just described there is an actual theory in chemistry called the Vesper model. It's how electrons basically kind of come to a sort of mutual agreement that, you know, I'll stay about 10 feet away from you, you stay 10 feet away from me. And then within that little sphere, we'll kind of zip around. But for the most part, we won't really get any closer than that to each other. Okay, so we kind of settle ourselves out. And that kind of creates these orbitals, these shapes in some respect. Okay, so let's take a look then and sort of focus in on this energy idea. And this entire slide is basically kind of encapsulating what I've kind of been talking about the entire time, right? So we have the Bohr model, which is schematic. And then we have the spatial situation, and those should not be confused, right? That's what they're talking about here. So when we're taking a look at an orbital or like the Bohr model, we're looking at an electron's energy. And depending on how this sort of tension between repulsion and attraction occurs between different electrons of different molecules, it will create a different three-dimensional shape for that particular molecule. Okay. At least as far as the cloud is concerned. Now, the important thing about energy, because we are basically kind of categorizing or characterizing the energy. This is kind of what it looks like, and this is going to be an important thing because remember, these are the energy topics are really, really important topics. So let's take a look at this. So first of all, we have our nucleus here at the bottom. I'm just going to put N, just generic for nucleus. Now, the first ring, now they're calling them letters, right? And this is kind of where I went to numbers. So this is my N equals 1. This is my N equals 2. Here's my N equals 3. This is my N equals 4. So when you're taking a look at each individual shell, right? So that's each ring is called a shell, within which you have a certain number of orbitals. What happens is the lowest shell is typically has different energies associated with it. So typically the lowest shell is the lowest energy. The highest shell is the highest energy. And then of course you have intermediate energies between them. And so basically what that means is if you are an inner shell electron, you are the lowest energy. So for instance, when we did our thing, I said I was an N equals 1, you're an N equals 2, and you're an N equals 3. You're the highest energy electron in the three of us. Right? I'm the lowest energy. I'm like the energetic sloth of the group, right? So you guys are like much faster. You're like much more energetic than I am. Okay. Now what that means is that's a different, what you are able to do is different than what I'm able to do. So energetically speaking, I'm in closer to this sort of scaffold, this energetic scaffold. Now, the reason why this is important is because of this, because of energy transfer. So what I want to do is I want to draw a consequence of this to kind of show you what we get out of this. So for instance, an electron like me, N equals 1, I can actually gain energy if you put energy into me. So if you put energy into me, I can absorb energy. But what's going to happen is I'm going to jump up to a higher level. Okay. Now here's the problem. If I'm wired to be a low energy electron, I can't hang on to that excess energy forever, can I? Eventually I got to let it go. And when it does, when I do let it go, I go right back to where I was designed to be, which is a low energy electron. That makes sense? So what does this do for us? Let's take a look at this. I want to redraw this a little bit, and I want to do just that. So here's a low energy electron. Here's my first level. And what I'm going to do is I'm going to beam some UV radiation. So that's energy. And what's going to happen is an electron, I am going to absorb that energy. And when I do, I'm going to be excited and I'm going to jump up to a higher energy level right up here. And instead of a negative, I have an asterisk. That basically denotes that I'm an excited electron. What does that mean? That means I've got my baseline energy, right, associated with my shell, 1, plus whatever energy I absorbed from the UV radiation. That extra energy has allowed me to jump in energetics up to a higher level where I have some decisions to make. The first thing is, what do I do with this excess energy? Well, I've got two choices. I can let it go. That's certainly a possibility, right? And when I do that, if I want to let that go, then that's going to come out as a photon of light. But I'm going to basically go right back down to where I belong. My original energy level, down to level 1. Okay. That process is what we refer to as fluorescence. So how many of you guys love to play around with a black light during Halloween? Right, you get the whole fluorescent paint thing going, right? You paint up your pumpkins, it's always awesome, right? Flash the black light on there, you can do all sorts of cool things, right? You take a look at it, and you're like, wow, that almost looks like it's glowing. Well, that's because it is. Because what's happening with fluorescent paints and things of that nature, chalk, whatever you have, is the UV radiation, which is high energy light, which is what a black light is. It's a UV radiation source. So it's going to bombard the electrons of the fluorescent paint. They're going to absorb that light. And as they absorb that energy, they're going to jump up in energy level, spend a little bit of time there, not very long. We're talking milliseconds probably. And then what's going to happen is they're just going to fall right back down. They're going to let that energy go because it's an unsustainable thing for it, right? It's going to let that energy go. And as they fall back down to their original energy state, they're going to release the remainder of what they were holding on to as a photon of light. So what you're seeing is actually literally a photon of light from the paint itself.
Can an electron be excited past like a shell that the element does not have for like?
So if its outermost is like a level 3, can it go to a level 4? Wow, that's a really good question. I would argue that because there's like nothing structurally associated with being on a level 4, you're just in a different energetic state. In terms of just the physics of it, I don't see any immediate reason, just on first, like off the top of my head, any reason why you couldn't. Because all you're looking at is just energetic levels. So if I really want to juice you up to like a level 5 or whatever, there's nothing that says you can't. It's not like the other electrons have anything to do with you. It's not like a committee of electrons saying, I don't know, they just put in an application to go higher than us. Don't know about that one, right? So it's like, well, I don't care. Because you're going to go up there, you're going to be spinning around, but you're just going to release it. So.
I want this question. If the outermost sphere is whole and you have this excited electron coming up there, what will happen? You're saying that you only can keep 8 total in the orbit, and you bring this excited one, what happens?
Yeah, right. Because I mean, that's obvious, because you can't just like pick and choose and say like, okay, I want to excite you, and everybody else, you guys just chill out, right? Just relax. Don't get so excited, right? So you're obviously, if you're beaming it at it, then it's obvious you're beaming it at all the electrons, right? So generally speaking, what you're usually looking at is that because all the electrons are differently in terms of behavior, typically speaking, they're probably also different in their willingness to absorb energy, right? So the reason why you say, for instance, get a single color of fluorescence instead of like a gamish of it, because different electrons would absorb different amounts because they're higher up in the spectrum. The reason why you only get one color is probably because that level is the most flexible to absorbing energy, whereas the other ones, as they're getting higher up in energy, are less likely to absorb it because they're like, you know what, forget you. It's like being hungry, right? So if you throw a piece of meat in front of a hungry dog, they're going to eat it. They're probably going to eat it more readily than the dog who's just fattened themselves up on an entire Thanksgiving spread. Well, maybe dogs are a bad idea because they'll eat themselves into a coma. But right, but I mean, the idea is, like you see this in the wild, where the wildebeest are like in front of the lion and they don't really care because they know the lion just ate their best friend, right? And they're like, you know what, you're going to be working on Charlie for a while, so you're probably not interested in eating right now. So, and I know that. So I'm not going to bust my butt trying to run away from you because I know that, number one, you're going to be running with Charlie in you now. So that's going to be an extra bunch of weight there. And you're already satisfied. So you're not really looking to eat me right now. All right. So there's just variations of how readily they're going to absorb light. That's the reason why you only get one light source emitted during fluorescence. Now that's cool, right? I mean, every Halloween, when time comes around, it's really cool because we get to play around with the black light. But it's biologically completely useless. I mean, unless it's like that's a survival strategy. I mean, if your thing is to like fluoresce at night as a way to warn predators that you're going to kill them if they try to eat you, I mean, that's something. But generally speaking, other than that, it's not really biologically useful. All right. Now, here's the other thing. You just dumped a bunch of energy into your electron, yes? And it's sitting there and you're wondering what to do with it. Well, how about this one as an alternative? Yep. Capture the energy. Don't let it go. Grab it. Grab that energy and put it to work for you, right? And then you're able to do all sorts of cool stuff with it. So rather than just letting it go, just grab it, sequester it, right? Capture it somehow into a usable form that you can then use to your advantage. That's kind of what we're doing every time you plug in your cell phone. You've got this energy electrical energy, which is coming to you in a form that's unusable. But we've captured it, haven't we? It's coming to us through the sockets. So what do? I need it in a different form, in a more chemical form that comes in the form of your cell phone battery, yes? So what you do is you capture it. You plug you siphon that off and you store it or you capture it with your cell phone battery so that you can do a time release as your phone is using the energy. Right? And that way we can do stuff like this. Yep. Yeah, so lithium. Yeah, it was just a little south. Back to 30, right? So that's an important thing, right? Because basically what this means is this is fun, but this is useful, right? Now, remember what we did. The first step to what we're doing is building our biological organism, which means what? What are the first things we have to do in our big biological questions of life? Survive, but we need something before that. Before that. Before that. Oh, before that. All these take what? Yes. So before you even get out this door, you have to come up with a plan, don't you? And that plan has to be kind of what parents always say to their teenagers. And how are you going to pay for that? Because that's usually the point where they realize that it's like, listen, we are now at a point in your development where it is your money that pays for it, not mine. Right? So I won't get there until probably I'm 100. But anyway, my kids know that too, so they know I'm screwed. But anyway, so there's that, right? So this is an energy plan. So this is what you want to know. Okay, great. If I can come up with a way to capture this, then all of a sudden we've got the ability to do some awesome stuff, right? That's basically what we're happening with solar panels. You come up with an idea to capture this energy, and now you're able to put it to work for you and do all sorts of cool stuff. So topic shift here. So that was basically energetics. We're still talking a little bit about chemistry now. In this particular case, we're going to talk about a specific subset of chemical reactions. And the reason why we want to talk about these is because it doesn't seem as quite shifty as at first glance, right? Because really what we're talking about and what we've been talking about is sort of this idea of energy, right? Laying down an energy plan. Well, all of that discussion comes in the form of cellular respiration. And in cellular respiration, what you essentially have in cellular respiration, metabolism in general, is a series of chemical reactions. And what do these chemical reactions all have in common? These chemical reactions are essentially all revolving around your energy plan. So when you're trying to do things like capture energy so that you can use it, those are all part of your energetic metabolism reactions. Okay. And so essentially when you take a look at your metabolism, that is to say, utilizing or capturing, sequestering energy in the form of a molecule, all of those reactions typically are being driven by a specific type of chemical reaction called a redox reaction, okay, which stands for reduction oxidation. And this is if you ever take chemistry, Chem 1, you guys talk a lot about oxidation reductions, redox reactions. Okay, so this is just a light touch of that. But basically, a redox reaction is a type of reaction that's set apart specifically with one particular type of behavior. That is to say that it is a chemical reaction in which electrons are transferred from one atom to another. Let's take a look at oxidation first. In oxidation, this is a situation that's happening when an atom loses an electron. So it's loss of electron. Reduction, it's when you gain an electron. So if you were to take a look at this, and always keep this in mind. Whenever you have a reaction where you're passing an electron from one thing to another, somebody's always losing and somebody's always gaining. Okay. Now, oxidation is the loser, reduction is the winner. Okay. So here is an example. I've got an electron. I'm going to pass it on. I've just lost it, yes? Oxidation. She just gained it, yes? Reduction. Now, if she passes it on, then she loses it, oxidation. She gains it, reduction. And if we keep passing this on, there's always a loser, loss of electron is oxidation, and a gainer. Gain of electrons is reduction. Make sense? I gained an electron today, right? So it's kind of like a relay sort of a thing. Now, one of the things that I always use in order to kind of remember this, and sometimes I'll always use, especially if I get a really complicated molecule, and I'm trying to keep myself straight, is I always remember this. Leo the lion goes grr. What does that mean? Loss of electrons is oxidation. Leo. Grr, gain of electrons is reduction. Grr. Now, if you take a look at our two atoms here, so here you have atom A and here's atom B. In this particular case, what's happening is atom A is taking an electron and it's passing it on to atom B, who gains that electron. So this one would be oxidized, right? So that's oxidation, loss of electron. And this one will have gained the electron, so that'll be reduction. Now, why are we talking about this in the case of metabolism? This is the reason why. Where did we start this conversation off? We started off the last slide, didn't we? We go from a conversation about what? Excited electrons, yes? To the capture of E asterisk, right? To the passing on of E asterisk. So if I have an excited electron, I can pick it up and I can pass it on. She can benefit from the energy that's in that electron. As she passes it on, the person she passes it on to can benefit from that. That makes sense?
Capture the benefit passing.
Yep. Well, and every time you pass it on, you benefit, right? So basically you go from capture to just a series of benefits as we pass it on. Think of it like this. I've got a big pot of gold. We're coming up on St. Patrick's Day eventually. I know we got to get through, Flower Day to get there. But eventually St. Patrick's Day comes along. And I'm not Irish, so just, I'll probably be, but I'm German. Right? The German day is in October. Right? But the idea is like just like the whole little mythical leprechaun Irish pot of gold thing, right? So the reason why is because you got a lot of coins, right? That's why. So let's imagine that the coin represents the electrons that we're passing on, and the coins represent the amount of energy associated with those electrons. The electrons have absorbed. So what I'm going to do is I'm going to say, like, you know what? I've got these excited electrons. I just captured them. So what I'm going to do is I'm going to take a little bit here, stuff my pocket with it, and here I'll pass it on to you. So now you take the pot of gold. You take a little bit, pocket it, right, and then you pass it on. And then you take a little bit, pocket it, right, and pass it on, and so forth. And so what's happening now is you're able to do a cut. Now, here's the thing. Now, we're probably going to go off and do whatever we want. Go buy our Bentley or whatever it is, right? So we're going to do different things. But imagine that we were all on a team and we were like, you know what? We need each other to be able to get this done. So we kind of have this partnership, right? This kind of work group. So we have to work together in order to get this one task done. And so I need a little energy to do my bit, and you need a little energy to do your bit, and you need a little energy to do your bit. And so if I get the energy, then I can do my part. And then if I pass it on to you, you get enough energy to do your part, and so forth. And then once we kind of take our cut on the energy, then we can work together to do our job, which could be like building some biological structure that allows us to do whatever. And so that's kind of what it is. So you're basically taking this energy and you're kind of taking a cut of it, and you're doing something that gives you biological capacity. Okay. Ah, if only. Right. So that's basically how that works. And that's kind of how metabolism works, right? So you basically have a series of metabolic reactions, redox reactions, where you have just the passing of electrons, energy, basically, eventually, right? But that's what's happening. So you're taking a cut of that energy and the electrons in order to build up enough energy to give you ATP. So let's say the three of us didn't have enough to buy the Bentley, right? But we're like, if I take my cut and then pass it on to you, and you take your cut, pass it on to her, she takes her cut, then maybe the three of us, because we're like Team Bentley, right? Our job is to go out and buy the Bentley. Right? But so then together, we kind of pool our individual resources to build up enough energy, so to speak, to be able to buy the Bentley. Right? And it's like we don't, in this case, it's like we don't own the Bentley. The Bentley just belongs to, the cell, right? So that gets used for another purpose. So maybe not a great fulfilling analogy, because we basically get screwed, right? We don't have any more money than we had before. We just have the knowledge that we bought somebody else a Bentley.
The Bentley's running though.
It's running and the cell's doing great, and the president of the college is riding high on our new wheels. But we didn't get anything for that. What do? We just go and take another cut from another pot, and we go out and buy another Bentley for somebody else. Yeah, that's basically what happens. Okay, that's essentially metabolism in a nutshell. In a very tiny nutshell, by the way. Okay, so elements. I told you we'd come back, didn't I? Elements. So the elements, these are the elements, obviously, right? So we've already talked about those guys, but here's the thing, right? So we already know that they're pure substances. These are always things that basically cannot be broken down into anything else. So what do we mean by that? What we basically mean is something like this. Is that an element? No. What is it? It's water, right? Can we divide that up into alternative substances? Yeah, we can. It can be either hydrogen or oxygen, right? So how about this one? Is that an element? Yeah, right. Because it can't be divided down into anything else other than oxygen, right? So that's an element, and that's actually how elemental oxygen exists, is diatomic. Okay. So those are the elements. That's the naturally occurring elements, right? So those are the ones that are associated with just being pure substances like that. Now, one of the things you guys have already keyed in on, and a couple of you guys have already mentioned it, was when we're doing our little ring diagram that we do, we notice that we fill some of these guys up, but that outermost one never gets filled up, right? Unless, of course, as you noted, the ones where you do fill it up, and that's kind of a different creature. We'll talk about that in just a second. But what happens with those outermost ones? Well, here's the thing. From here on out in biology, we are immensely interested in really one zeroed in particle. So not only are we not interested in protons and neutrons, that's nuclear physics, we are not even interested in all the electrons. And that's our thing. We're only interested in one type of electron. Which one? Yeah. And what do we mean by valence? Something you hang on your windows? That's valence, actually. It's slightly different. No, so what is this one? The outermost electrons and the outermost shell.
So on the sodium section will be that one that we left out.
Just the one, right? Now, why are we only interested in these guys? Huh?
They're low.
They're very lonely. At least that one is, right? But what if you have 6 that are out there, right? Go ahead, you say.
Because of redox, correct?
But the passing on electrons. So you can get redox between oxygen and other ones. So they don't just have one. So there is part of that, right? So those outermost ones are certainly targets for kind of swapping back and forth, right? But that is part of it, right? Good. they do have the most energy, right? And typically because they have the most energy, they're easy to let go. That's certainly a big thing, right? But you're not going to want to let all of them go. Because if you have oxygen, which has 6 valence electrons in it, if you let all your electrons go, your valence electrons go, you would have like a positive 6 ion. That would be like crazy. I mean, you'd be like so charged that you'd almost be like a little lightning bolt everywhere you went. So just chemically, that would make you kind of a little odd if you had that much positive charge on you. So why? It's because of all the electrons, these basically determine chemical temperament and personality. You, by virtue of your goal to build a biological organism, are a molecular matchmaker. It is your job. No eHarmony, no Match.com, none of that nonsense. None of the sketchier ones, which are a little scary, right? So no, it's old school. It's you get to know people and you try to connect people like the way it used to be done, like way back in the day. Like so far back that I wasn't part of that generation, but that's how it used to be. You know, it's like, oh, I know somebody, so-and-so's great uncle's cousin who would just be a perfect fit for you. Right. Right. So that's, and then of course they would set you up and then it would be weird and helpful at the same time. Right. Because if you're like back in that era, there's like, I mean, the closest human being is the family cow that lives 40 acres away. I mean, it's like there's nobody around you, so pickings are quite slim. Right. By the way, which is an interesting phenomenon, geography is an interesting phenomenon when it comes to population genetics. Back in the day, we used to marry people not because we really liked them, but because they were close. And there was no prospects that you were ever going to get out of your little area. So it's like, hey, you know what? You're not like terribly repulsive. So I guess I'll just marry you and it'd be easy. We all live here and we can just, that sort of thing. Pretty depressing, right? Yeah. Anybody want me to be their matchmaker? It's like, yeah, the answer is no, by the way, to that. So I'll just answer that one for you. The answer is no. Not volunteering, but anyway, right? But I mean, that's the way it happens. You can tell that. You know how you can tell that? You don't have to go very far. Just go to one of those old like agrarian villages or areas like that in like just like rural America and look at their cemeteries. Like an old farm town, like where it's not very big, and just look at their cemeteries. You'll see, oh, well, here's the Smead family that clearly married the Smith family, and this was Smead and Smith together, and you can see like it was just one farm family that was in the area marrying another farm family, and that was pretty much it. That's how generations happen. So you can actually see that. By the way, that's not just in America. You can see that in any area, rural Germany. You can see it rural everywhere else. By Germany, I'm thinking Bavaria. Things like that. That's because they've got a reputation. The Bavarians, gotta bless them, right? So all things Oktoberfest come. So, but that's kind of rural. I mean, rural France is the same way. You look at some of their old cemeteries, the same basic idea. You got these families marrying each other, and that's kind of how it is now. So, think about that, by the way, especially now in this generation, because we're like so interracial now. It's like not a big deal. Like interracial marriages, we're just so used to just like marrying into different racial backgrounds or customs or cultures. It's not even a thing anymore. That is an exceptionally recent development. Exceptionally recent. From a population genetic standpoint, it's a healthy development because we are better together than we are apart. That we get a little weird when we come apart. We're much more stable as a group and as a people, and all things good happen when we kind of learn how to play together. But that's a really recent development. So like population genetics going forward is going to be really interesting. So a lot of heterozygosity going on. That's a good thing. So So basically, these are the outermost, right? So they have a particular temperament and personality. But then what if you kind of get back to Raphael's point, what if you have all full, right? So your valence is all full. That basically means you're inert. Okay, let's take a look at that, right? So you have basically 8 electrons in your outermost shell. Guess where those guys are? Group 8, far right on the periodic table. Now they don't all have 8, right? Helium has 2 because it's only got 2 electrons, right? But that fills up the first shell, right? Everybody else after that fills up the second is for neon, right? So it says first and second is full. Argon, first, second, and then the third one is full, right? And so forth. Krypton, xenon, radon, and so forth, and whatever argonium is, right? That's made in some lab in CERN somewhere. Yeah. So that's not really real. So radon we get to, that's like one of the last. So the naturally occurrings are like right around in this area here. That's mostly what we have. I mean, these guys are obviously naturally occurring, but they're not very common. So go ahead.
Why is nitrogen constant rather than some color that's far right, bro?
So for these ones, so this is a chemistry's chart, and usually when you see something like that, they are highlighting like some sort of chemical behavior in particular that they're going after. Without knowing exactly which trait they're going after, why they're highlighting it, I could only guess. But yeah, in terms of electron structure, that's not what they're highlighting. There's something else going on there that they're focused on. Because you can see like mercury and bromine are also highlighted. Generally speaking, usually, actually I can guess, to be honest with you. I think what they're highlighting is the differences in the states of matter. Right, because metal are solid except for mercury, which is liquid. Bromine, which usually that group 6 is, or excuse me, group 7 is usually gas. Bromine's a liquid, right? And the noble gases, which are group 8, are all gases. And normally these are liquids and solids, depending, but these guys are gases. So nitrogen, oxygen, fluorine, chlorine are all gases. So I think what they're trying to do is highlight the difference between gases, solids, and liquids in natural state, if I had to guess. So, and I think, yeah, that's, I can't believe.
Would there be, I don't have this memorized anymore, should I?
The periodic table?
Yeah.
Why would you memorize in the first place?
My teacher made
I
me
would,
years ago,
yeah,
so
I would,
I-
yeah, even like when I went through chemistry, I'm like, no, you always have this on hand as a reference source. Don't memorize this. There's better things to memorize. You don't need to memorize any of this. You get to know it pretty well because you work with it a lot, but for heaven's sake.
So I don't really need to worry about that too much. Okay, it'll come to
No.
me like knowing everything.
No, yeah. So yeah, and if there's something like on the exam or something like that, where it's like, okay, I want you to work with sodiums, electrons, or something like that, and then you know, my intention is for you to have a periodic table as a reference source to take a look at.
Okay.
So yeah, I don't. That's yeah. Wow. Who would do that to you?
His name's Ken Burchett. He's my
So I-
chemistry teacher.
So I see you didn't like him.
Yeah, we never see eye to eye.
I wouldn't either if he was making me, because even when I took chem, even at UC Davis, when we took chem, you weren't required to memorize the periodic table. That's just insanity. The periodic table is not what you see on the periodic table. Actually, this is pretty scaled back, right? When you take a look at this and you get into this in Chem 1, as you get deeper and deeper, you'll notice that when you run into these physical traits that you're studying that adhere to what's called periodicity, that is to say that they're predictive across the periodic table, it's actually quite amazing because you can actually take a look at the chemical properties of these elements and you can predict them from the periodic table. Literally, their chemical properties and their chemical behaviors can be overlaid, like almost like you've got the answer key to the universe, and you can overlay all of their chemical properties and all these amazing bits of information, and they're completely predictable by the periodic table, just like layer upon layer upon layer upon layer upon layer. That's the reason why the periodic table is not worth memorizing. Because a chemical, one of the best the periodic tables I've seen has so much information in. I mean, literally, the elemental symbol is like tiny, like 0.5 microtype. I mean, it's like, and there's just like information everywhere in the box. I mean, just all over the place in the box. And it's like, and it's basically just a ton of information in there that you can actually, so that would be like, where do you stop memorizing the periodic table? I mean, that's just kind of brutal. Now I can, maybe memorizing some of the common ones like zinc. You should probably know zinc when you see it, magnesium and things like that. But the whole thing, no. That's trivia knowledge that is going nowhere, because this is an ultimate like resource for you. Okay. Spoken like a true biologist, right? Of course, Dr. Dillon would probably treat. No, I don't think he even makes his. I don't know of anybody in our chemistry department that makes their students memorize the entire periodic table. It's just use it, yes, but not memorize it, right? Because it's actually more powerful to use it than it is to memorize it, because you're only going to be able to memorize a little bit of it, and then you're done. But if you have it in front of you, you're going to be able to really use that thing very powerfully to solve a lot of good problems. Okay, so these guys are full, yes? They have all 8 or 2 in the case of helium. Everybody else does not. As a matter of fact, we already know sodium, yes? We've already come down to sodium, so that one only has 1. Well, let's take a look at the polar opposite. Let's go to chlorine, right? So this is group 7. So how many electrons does chlorine have? Okay, let's go ahead and start mapping them. So I've got 2. Am I done? Okay. What do I do here? Okay, now what? Another one, and how many? Am I done? Okay. So how many valence electrons do I have? How many did I have in sodium? So this is group 1. This is group 2. The other transition. Group 3, 4, 5, 6, 7, and 8. So when you actually have the group numbers, they're actually labeled by the number of valence electrons. Guess what? The ions that it makes is the opposite of the valence. So how many can I put in this outermost shell in chlorine? 1. So if I do add 1 in there to fill it all up, how many electrons do I have? And how many protons do I have? What's my charge? So group 7 makes a -1 ion. An anion, right? How about oxygen, group 6?
2.
So you add 2 more electrons and you're going to make
Anion with a
-2 charge, right? How about nitrogen? Right? Carbon? So it's got 4 and 4, right? So if you add 4, you can lose 4. You can go either way, right? So you could be either positive or negative. But are you likely going to make a 4 charge? No, right? So at that point, you're getting weird, right? So you're probably not going to make that. But boron is going to be what? Yeah, +3, right? Because now you've sort of flipped the script. You're on the other side, right? Magnesium +2, and sodium. So your ions are related to your valence electrons. Why? Let's take a look at this. The most important thing to understand about these valence electrons, even more so than the fact that they are valence electrons, is the octet rule. Because the octet rule is associated with the valence electrons, but this is basically what drives chemical behavior of the valence electrons. Now, if you're an atom, you have a holy grail that you're looking for. There is a goal and an endpoint in your existence that you are looking for. It is like your atomic nirvana, your state of ultimate perfection, for which you will never be satisfied until you reach it. And that is the octet rule. This basically means that all atoms strive to achieve a complete outer shell. By either bonding with other atoms or gaining electrons. That's losing / gaining. That's what that tried to squeeze in there. So here's the thing. There's only one group, group 8, that's perfect. Everybody else is in a state of psychotic disrepair. Now, the further away you are from perfection, actually, the more stable you are. The closer you are to perfection, oh, but just short, the more crazy you are, the more desperate you are, right? Think about it this way. Imagine being close to the finish line in a race. And this isn't just any race. This is like the Olympics. I mean, you've been basically funneling your entire life into this. Your whole life has been nothing but training for this moment. And luckily, you've made it to the Olympic team, right? But you've lost a few times. And it's been heartbreaking, right? So you're one of those feel-good Olympic stories that we all like to watch. Oh, so-and-so's fell on the ice about 25 times, so maybe this time they'll actually get it, right? Because after all, they've done a great job everywhere else, so why not finally put it all together in the Olympics and finally walk away with your gold medal? Dan Jansen, for those of you who are speed skating fans, is an example of that. That was particularly poignant because Dan Jansen was a great speed skater everywhere else except for the Olympics. So, I mean, he won like world championships, he won all sorts of stuff easily. I mean, he was clearly the best. And then just weird flukish things would happen, like he would just slip and fall during the Olympics and it'd disqualify him, and it would just be heartbreaking. And then finally, like his last Olympics, as he was getting older, he finally put it all together and he won actually a couple of gold medals. So it's like really satisfying. It's like, oh, finally. Right? It's kind of John Elway for you Broncos fans, right? How long did you guys suffer and toil in the desert wilderness of oblivion as John Elway single-handedly hauled the Denver Broncos organization like a dead carcass on his back to the Super Bowl 4 or 5 times in a row, only to lose it because after all, we realized that we needed an actual team to win the Super Bowl, not just a quarterback. Spoken like a true Raider fan, right? But finally, guess what? They put the team together, didn't they? They got him a running back. They got him a decent defense. They got him an awesome offensive line. And then what'd you guys do? You didn't just win one. You like went back to back. I mean, during a particularly difficult time. A lot of good teams, by the way, in that era. Not just the Broncos. So that was like one of those things where it's like, you know, Elway finally, and even the people who didn't like Elway, like the Raider fans, it was like, you know what? Finally, I mean, we hate to see him in Broncos uniform winning it, but you know what? I mean, there's just something wrong with the universe when somebody who's been good for that long and carried an organization for that long doesn't get their moments, right? So that first Super Bowl was, I think, like cathartic for a lot of folks, especially for the Broncos fans, no doubt. Right? But that's kind of what we're talking about here. So you get desperate, right? Because you've basically been your entire life and you get so close and you're like not there, right? And so finally, here you are, right here, literally, you're like right there. You're neck and neck with your hated competitor, the Oakland Raiders. I say for you Broncos fans because I know how you guys feel. Actually, how the whole entire AFC West is. But anyway, except for the Raiders, of course, that we like ourselves usually, right? So it's complicated, but right. So here you are, right? Literally, you're so close to the tape that you can like smell the plastic, right? That kind of hot, plasticky smell that we all love in the summer. You know what I'm talking about, right? Right? You're so close. You're like You're looking on the side of your eye and you can see the skull and crossbones right next to you, just about ready to Hail Mary it over the line. And you're like, right? Oh, no, you're not that desperate. No, actually, you're more desperate than that. So here's what you do. You actually cut your tongue off and throw it. Because that counts. It was part of your body. Technically speaking, it's still warm, right? So it's still technically part of your body. So you cut your tongue off, you throw it across the finish line, and you win. And not only that, but guess what? You beat your arch nemesis, the Raiders, to do it. Is there any outcome or any scenario more satisfying for a Broncos fan than that? To beat the Raiders, to destroy the Raiders, and to take home the championship. That's probably the most satisfying scenario that any Broncos fan could imagine. Right? Just like it is for the Raiders if we beat the Chiefs. I would argue probably it's also the same for the Broncos fans, because I think it's been longer since the Broncos fans have beat the Chiefs. That one's been depressing, actually, a little bit to watch. Trust me, we've had the same thing. It's called the Schottenheimer years of the Chiefs sets. We couldn't beat the Chiefs for the life of us. All the gnomes and the minions in the world were against us. But anyway, that's what happens. Now, what happened there? That's desperation, right? You are so close, you're willing to do just about anything to get what you wanted. Now, think about it for a second. The teams that year that were 8-8, were they that desperate? Were they willing to cut off their arm and throw it across the finish line? No, because they were kind of middle of the pack, right? I mean, they were neither here nor there. They were all right. They were great. They were bad. They got some work to do. But they're not desperate, are they? So they're happy with where they are. Or I shouldn't say happy, but it's a little different, isn't it? So that's the reason why we love the playoffs, isn't it? Because the playoffs are so exciting in all playoffs, in all sports, by the way. Stanley Cup, it wasn't that long ago, was it? We were all like super amped up as a city, right? As the Avs marched their way to the Stanley Cup. Why? Because we realized that everybody was much more desperate now because everybody wanted to win. It wasn't just like regular season where it's like, win them, lose them, that's fine. We're somewhere in the middle, whatever, right? It was like, no, we got a chance here. We are so close. We can smell it, right? So you're even more desperate to get there. You can feel that desperate. That's what makes that whole playoff thing so fun. That's the reason why we love it so much. Okay, is because of that desperation. Now think about it. The guy who is about maybe 10 back and running this race, are they going to be cutting their tongue off? No. Why? Do they have a realistic chance of winning? No, not at all. Right? This person's psychology is going to be a little bit different, isn't it? They're going to be like, you know what? I'm running about 10th right now, but maybe if I kind of really put some leg into that final sprint and that final stretch, I might be able to take 9th, maybe even 8th, if I lean into it a little bit. And, you know, if I get into that sort of 5 to 8 range, it's not so bad, right? I'm okay with that. That's a pretty good place, right? That's a good place to build on. I'm okay with that. Notice, total different psychology, are they? They're not desperate, but they certainly are trying to do as best as they can. The same thing is also true for the elements. So here you can see your periodic table, and you can see that the closer you are, the more psychotic you are, the more willing you are to cut off your tongue and throw it across the finish line, right? Now, the guys who are here in the middle, like Carbon, for instance, are much more well-adjusted. They're all like, guys, first of all, I could either go 4 up or 4 down. It doesn't matter. I'm like right in the middle of the pack. So either way, whatever. Do I need to do some work? Yes, just like an 8 and 18. Do I need to do some work? Yeah, I'm going to go through free agency. I'm going to sign some people. I'm going to try to get better, all that sort of thing, right? So we still have some work to do. But I mean, am I like desperate? No, right? Like apparently the Bengals were when they cheap shotted Mahomes. But anyway, love to see the Chiefs lose, but I don't want Mahomes to get hurt. So I want him to be around so we can beat him fair and square. Same thing for you guys, right? You Broncos fans. You want Mahomes to be around so you can beat him fair and square, because it's more satisfying to beat the guy when he's at his best than to sort of get a cheap win. Unless, of course, it sends you to the Super Bowl. Then in which case you'll take the cheap win. Right? So I think that's what the Bengals are going for. But anyway, it didn't work in their favor. Anyhow, right? So what this does is I want you to take a look at this relative to some of these psychologies. And I want to take a look at, first of all, chloride and sodium, because they have two very different personalities. Both of them are very close, aren't they? How many valence electrons does chlorine have? 7, right? So here's what we do. Since the valence electrons are the ones that are defining the temperament, right? The chemical temperament of these atoms, they're also the ones that are involved in bonding. So because they're the ones we're really focused on like a laser beam, we tend to have, and we learn this in chemistry, we tend to use what's called the electron dot diagram, right? Which is essentially just a schematic. It's just a notational system that helps us focus in on just the valence electrons, because those are the ones that we care about. So we have 1, 2, 3, 4, 5, 6. Wait, 3. Okay, that's no there. 6. Ignore that one. It's a little mutant right there. So 6 and 7, right? So that's the electron dot. Now, what about sodium? How many does it have? 1. So it's got 1 valence electron, right? So what does sodium need to do in order to become perfect? Could it add 7? Yeah, it could, right? I mean, it could acquire 7, right? To fill up those 7 seats. Which one do you think is easier? Getting rid of 1 or gaining 7? Probably getting rid of it, right? So in this case, what happens? You get rid of that 1 and you fall back on the next lowest one, right? Which is full. So if you're able to get rid of that 1 electron, you're perfect. You've just achieved nirvana. So you've just basically acquired what you wanted all your life. How about chlorine? What does it need to do? It needs to gain 1, right? And so once it gains that 1, then it's going to have 8. It'll have become perfect. And then it'll have everything it needs. It's perfect, right? So it'll have everything it needs. Now, here's the thing. Because they're so close and they're so desperate, these guys are very reactive. That basically means they're willing to do anything to anybody for any reason to get that electron if you're chlorine, or to get rid of that electron if you're sodium. So I always like to anthropomorphize these because we associate better with that, right? So imagine chlorine kind of like being sort of lurking behind a dumpster in a dark alley, waiting for some poor suspecting atom to walk by so that it can jump on it, grab its electron, take it, and then it'd be like, listen, this is mine now. I'm satisfied. I'm perfect. I don't know about you. Screw you, right? So it doesn't really care. So it's going to be perfect. But here's the problem. It doesn't have to do that, right? Because sodium is right next to it. What is sodium trying to do? Yeah, it's basically looking at that same person walking by. It's like jumps on him. Well, in this case, it's like, take my wallet. I don't want that money, right? That's a little crazy, but that's what sodium's trying to do, right? It's like, take my money, please. It's like burning my soul. Take it. I don't want it. Get rid of it. Of course, that's weird, right? But we have no association with that whatsoever. But that's what sodium's trying to do. Well, the nice thing is, guess what? Sodium and chlorine are basically right in next to each other behind the same dumpster. So it's like, sodium, why don't you meet chlorine? Because as badly as you want that electron, chlorine wants to get away. Right? So sodium basically says, hey, guess what? I've got 1. I want to get rid of it. So why don't I just basically give you mine and you can hang on to it. And that way I can live my existence minus an electron, which means that in my happy place, I am what? I'm perfect. That's true, right? Because I fall back, but I have 1 less electron, which means I am not inert. I am an ion, right? Because that means I would be in a +1 state, right? Because my electron has now gone on to chlorine. Chlorine, on the other hand, since it gained that electron, would be in a negative state, right? So it'd be a negative ion. So that's its happy place. And so that's an example of these two guys coming together to basically form another molecule.
Is this considered the redox?
Not so much, because they're not necessarily passing on electrons, they're sharing them. So it's a little bit different. So passing on electrons is something that we usually see. You can actually, there's like a flow of electrons coming through, where they have their own valence electrons that stabilizes them as a molecule, but then there's like a series of electrons that sort of flows through all these outer shells and kind of like makes their way through. So you kind of own one for a little bit, and as it kind of flows through, you pass it on. That makes sense. So basically now what's happened, is sodium happy? Is chlorine happy? They've achieved their octet rule. But guess what? They've only done that within the context of what? A bond with each other. So as long as they are associated with each other, they're happy. So that is a bond. That's what we mean by all atoms strive to achieve an octet rule by forming bonds with each other, or sharing or gaining or losing electrons. And that's what drives chemistry. Now, the thing is, the cool thing about that is the only ones that aren't playing that game are these guys right here. Everybody else is in varying states of crazy. The more crazy you are, like these guys here and these guys here, the more reactive you are. The more kind of middle of packish you are, the more kind of relaxed you are. Carbon, for instance, is you're going to form bonds with carbon, but carbon is pretty chill. It's like, hey, I'm right in the middle. I could go either way. I could go 10 back. I could go 10 up. At the end of the day, I'm right in the middle. So it's not like I'm a threat to win. I'm not really a threat to lose. Right. So I'm 8 and 8. Right. And that's what carbon is. And so that's basically how that works. That's the reason why carbon is so stable. That's the reason why, by the way, you're made out of carbon. Is because the last thing you want to be made out of is a lot of volatile, chemically temperamental atoms, because then you would be a little on the, on a physiological level. That was a little performance art, by the way, if you're reviewing this as a recording. Just imagine what it looks like. And
I was just wondering, how did the happy couple know how do they know how to find each other to form the bond? Is it just,
sodium and chloride?
yeah, I mean.
Well, they don't, right? Because they form a bond with just about anybody. So sodium will form a bond with potassium. I mean, not potassium, but bromine, iodine. It could form it with oxygen. It could form it with anybody, actually. It's not really picky. And that's where you get all these different molecules. So, I mean, like, for instance, you could have potassium forming a bond with chlorine, or sulfur, or phosphate, or oxygen, or fluorine, or any of those. Any of these guys, particularly here with any of those guys over there, for the most part, you see them all in nature.
Do they both have the needs to give and take?
They each have to complement each other, right? So, and none of that, but it doesn't have to be like one. So, like, for instance, if you have a calcium chloride, right? So calcium is +2. That means it's got 2 positive charges. That means it has 2 valence electrons to deal with, to get rid of. So it can form a bond not with just 1 chlorine, but 2 chlorines, right? Or technically speaking, there's nothing that says it can't form with oxygen, 1 and 1, right? Or it could form it with different things. It could form one of those bonds with chlorine and one of those with fluorine. There's no, just because I form a bond with you to share electrons and I have other electrons to share, I can form other associations with other atoms. Now, when I have that, it's like sister wives, right? It'd be like, okay, so you guys don't all necessarily get together as a group of atoms. So some of you may conflict with each other. So maybe less likely that I form a pair, like, one with chlorine and one with this, because you guys kind of conflict with each other. It'd be more likely to form it with, having 2 chlorines, for instance. And it depends on what those chemical interactions are with those bond partners. That makes sense. Some of those will be more stable. And the reason why I pick on sister wives is because that's been a train wreck of a drama that's, I don't know, some of you guys may watch that show. It's hysterical. But I mean, it's like everybody who first watched the first show of that one, which I think I've only seen maybe parts of one. I mean, it has train wreck written all over it. I mean, from top to bottom. So the fact that his wives, I guess, are kicking him out to the curb is not surprising. What is surprising is it took him this long. Any Sister Wives fans out there? Yeah, it's kind of funny. I mean, it's like something that's, I guess, technically supposed to be illegal, right? Polygamy. At least, I don't know if it's, I don't know if it's a federal thing. It must not be a federal thing. It must be like a state level thing, but it's just, you know, you don't, that's not the sort of thing you expect to see like a TV show on. Yeah, I don't know. It's just, it's funny for a lot of different reasons. But anyway,
Sorry, before you move on, I just wanted to ask about sodium. So we usually hear in the supermarket like ionized salt and non-ionized salt. Is this what we're referring to?
not ionized, iodized.
No.
It's different. So, and the reason for that is because what they do is in natural salt, it's just sodium chloride. That's all it is. But when you iodize it, they actually add some iodine into it. And that's an additive. So salt doesn't come iodized. Natural salt is nothing. We usually add iodine in it. And there's a reason for that. It's because we need a certain amount of iodine in our diet, a little bit. And that's so that we can make our thyroid hormones. Because our thyroid hormones are actually, they actually make, that's the one use of our iodine that we use, is they incorporate iodine into those thyroid hormones, and that regulates your metabolism. Yeah, and that's the reason why, because the idea is if you don't have iodine in your diet, then you're not going to be able to make functional thyroid, and your metabolism is going to start getting all out of whack. And so your metabolic baseline, that sort of is your, sort of like your background metabolic rate, is going to be completely dysregulated. And you don't want to make your thyroid unhappy, because when you have your entire, because that's your entire, not just a little bit of metabolism, that's like your entire systemic metabolism, right? So what you now know as sort of like what your life existence is like on a normal day is largely your reality set by your metabolic reality set by your metabolism, which is set by your thyroid hormones. So if you jack with those thyroid hormones and your metabolism starts to get screwed up, then the way you feel normal is going to be completely out of whack, and you're probably going to feel pretty cruddy. You're not going to feel normal because your metabolism is going to be like in some other place that you're not used to it being.
There's no other way to get iodine?
We don't have iodine typically in diets, in our diets. That's why we have to add it in there. That's, by the way, one of the reasons why animals, a lot of mammals in particular, have an instinct to salt lick, is because they, a lot of times, some, not all natural sources of salt will pick up just a little bit of iodine in the production. And so if you lick habitually salt, then you'll get, it's not a lot. You don't need like a, you don't need like a big horse pill of iodine in there. That's not, you don't know, you'll kill yourself there. Right, so you just need a little bit of it. And like if you're salt licking all the time, like deer do all the time, habitually, constantly, then they'll pick up usually enough iodine to give them what they need for that purpose. So that's why you want to buy the iodized salt. Yes, because that'll make sure that you have sufficient iodine so that you can make your thyroid hormones. If you don't buy the iodized salt, then you need to make sure you make it a habit of going out there and licking salt licks, just like any other mammal.
Do
Right.
you know what we did before civilization and like
We had raging thyroid problems, probably. That's more than likely what happened. And that probably just spins out of control into all other types of healthcare issues, and we didn't know anything about any of them. So pretty much if you just died of something, it could have been anything from a heart attack to diabetes to stroke to thyroid related issues. If people were overweight, it could have been a thyroid issue. I mean, you've got lots of literature in the past about goiters and just huge, I mean, all sorts of things going on, and there was really no solution to it other than just, you know.
So we used to die like at 21.
Oh yeah. No, we were not great at lifespan back in the day. So life and the quality of living probably in the past, even in the recent past, probably sucked like a Hoover. I mean, seriously. I mean, if you consider how much healthcare you guys have now, you guys live like kings. It just, what healthcare must have been like even just 100 years ago was just an absolute train wreck. I mean, just think about teeth care. How many dental hygienists in the crowd? You can admit it. Hands up, we need you, right? You're like, no, I'm not gonna do it. But just think about it. Think what you have to do to maintain your teeth, good hygiene, right? Brushing, flossing, rinsing, all that sort of stuff. And if something happens, what do? You go to the dentist, they can drill it out, fill it, you're right as rain, you're ready to go. If it falls out, not a problem. They can crown it, they can bridge it. They can even give you dentures if you have to, if it all comes out, right? So that's always a thing. But back in the day, guess what? You had a toothache? Sorry. Sucks to be you, doesn't it? Yeah. I don't know if you guys ever had a dying tooth. Anybody ever have a dying tooth? Yeah, it hurts like hell. I mean, it's like one of those things where, like, remember when I talked to you guys in lab about our tendency to implode as mammals? That's one of those implosion moments. Because I remember when I got one crown. I remember when that tooth was dying. I mean, it literally, it hurt so bad I couldn't actually close my mouth. I couldn't sneeze because there's a little bit of a tooth clap when you sneeze, and it would just be like your mouth would blow up. And not only that, but I couldn't eat. Lost a lot of weight then. And I couldn't even talk to like my wife. She'd be talking to me and I literally couldn't concentrate because I'd be like trying to like hold my mouth still so that it wouldn't hurt so much. And that was with dental care, right? So imagine that's your life and there's nobody to go to. There's no way out of it. There's no way around that. You just live with it.
They give you a lot of cocaine.
A lot of whiskey, right? I mean, that was anesthetics back in those days. Just drink. And if you can't remember it, then it doesn't matter if you're screaming while it happens. If you can't remember it, then you're all good, right? I mean, that's kind of what it was like. So if you think about it, and I always think about this, like, not just like 100 years ago, but I think about this, like, back when the Romans were around. And, you always look back at this because we're such a peaceful by relative comparison, we're such a peaceful generation these days. I always think, why would anybody want to go to war? I mean, why would you want to get shot? I mean, that has got to be like the most horrible experience I could think of, right? Why would you volunteer to do that, right? Like, and then I go back, like, why would a Roman, like, not just volunteer to do it, but like insist on going back and doing it again and again and again? When they had to basically, I mean, you can imagine they're getting wounded, they're getting these giant slashes in them, and it's like, and you go back in it for some more. It's like, what drives you to do that? Why would you do that, right? But I was thinking about, it's like, well, it depends on what your quality of life was like. Think about all the mental health issues we have now. Depression, right? Anger, suicidal thoughts. Back in those days, hey, funnel that all into, you're my enemy, and I'm going to take it all out on you, right? Oh, no, let's keep going. How about pain, right? We talked about tooth pain, but what about other sicknesses and things like that, right? I mean, if you have like shoulder pain because you dislocated a shoulder, guess what? There's nobody popping that thing back in. You're living with a dislocated shoulder for the rest of your life. So you have all these pains and they're screaming pains. Everybody have a dislocated shoulder or any kind of a joint damage, right? It hurts, right? I mean, you're like, oh my gosh, this pain is like, this is all I can think about. But guess what? It's like you get to the point where it's like, you know what? My mouth is a train wreck. I just feel like my head is a train wreck. I mean, my shoulders are dislocated, my knee perhaps, because I mean, battle is a physical effort, right? I've got all these slashes and open wounds everywhere. I've got, I mean, just this train wreck of a body that's hurting badly. And you're like, you probably get to the fatalist point where it's like, what's the point? What's the point of living? Because right now, to live sucks. To die in battle is glory. So what's better now? To live a sucky quality of life or to charge the hill? So that's how bad life quality could be back in those days. We usually think of all the rich people back in those days because those are the people that write all the histories. But the average Joe, their quality of life probably sucked. I mean, just really bad. I mean, like worse than anything we know of, which is always, I like to take that. That's just my thing, as kind of a little bit of a gut check. When you are hating the world as it is now, just remember the world has been a lot worse not too long ago. just keep that one in front of you. That's my father knows best moment, but anyway. So what I want to do then is next time I want to sort of talk a little bit about some of these elements, right? Because we have all these elements, they're all naturally occurring, but do you guys have any gold in your body? Well, not unless it's not normally. I mean, obviously teeth, maybe. Some of you guys may have gold fillings or whatever, you know, kind of stuff like that. But normally speaking, no, right? I mean, you don't have gold ions and stuff like that, right? Because gold is fairly inert. I mean, it's kind of inert for where it is actually, right? So do you have a lot of silver in you? Yeah, no, not so much. Teeth, notwithstanding. Do you have a lot of mercury in you? Yeah, that one you have, yeah, unless you've been eating fish, right? Bad fish, I would say. Right, so normally, no, right? You don't have these things in you. So, well, then what is in you, right? So if you're taking a look at all these naturally occurring elements, then the question is, what really do we need in order to build you? And actually that list of what we need naturally is amazingly short. As a matter of fact, just to kind of scope this out, this essentially is you on an elemental level. On an elemental level, this is basically what you are made of. And as a matter of fact, we can go even further than that. So all of these naturally occurring elements, 4 of them, make up the overwhelming majority of what you are. What are those 4? Carbon, hydrogen, oxygen, nitrogen, CHON. Those 4 make north of 96% of the atoms that are inside you right now. So of all the 90, we can boil it down to this list, and of all of this, the overwhelming majority comes down to 4. That's kind of crazy, right? So this is basically something that what I want to do is I want to kind of sketch that out, because this kind of blows students away a lot of times, right? Because we think, oh, these are all naturally occurring, so they must be in us. Like, no, we're not made up of we're just the tiniest fraction of all the naturally occurring elements that are out there. Okay. And so this is kind of cool, because basically what this means is we can focus all of our studies around the chemical behavior of really 4 different atoms. That's manageable. So we can take all of our chemistry, eventually learn some of the basic principles across the board, but then we can sort of zero like a laser beam on those 4, CHON. And we could understand a good chunk of the chemical behaviors behind what essentially is going to inform a biological organism. That makes sense? So we say all that to say CHON, right? That's basically what we say. That makes sense? So that's what I want to start with. And then we'll kind of move forward with our chemical bonds after that.